All right, so we're joined here today by Giang Nguyen, who is a exoplanet weather person, I guess you could say. Is probably a more accurate way of describing it. Is that,
Yeah,
is
yeah,
that correct?
a
Or
forecaster.
right. And why is it that you're a forecaster?
It's actually it's because I predict what's going on, but it's kind of ironic in a sense too, because it's 200 light years away. So you're actually looking at the weather 200 years ago, which might not be forecasting per se. It's backcasting.
Back, I like that. Yeah, not forecasting at all. It's no foreshadowing. It's already happened. So tell us a little bit about. Uh, I always get this one wrong. K2141b. Tell us about that.
Yeah,
Did
yeah.
I get that right?
Yeah, yeah.
Okay.
It is
Nice.
correct. You probably do have the paper in front of you, so you can just glance over and check.
Yeah, I was looking
Uh,
for it, and I'm like, oh, yep, that's
it's on the
right.
title. That's the title. Yeah. Yeah, so it's a recently discovered exoplanet. So it was discovered by Italian researchers in 2018. So it's a super Earth. So it's like a slightly bigger than an Earth-sized planet, but it's still pretty small in the grand scheme of things. If you compare to Jupiter or Neptune, that are like 10 times bigger or 100 times bigger than Earth. So yeah, so it's like an Earth-sized planet that orbits very close to its star. And so you know the talent team put out this newly discovered planet. It was very easy to discover to observe it because it has a very fast orbit, so it makes a lot of orbits, and so you can detect it through the dimming and the brightening of the star whenever the planet goes around it.
Right.
Yeah, and so then I set out to, or we set out to try and see what the atmosphere on this planet is like, and we discovered that since the planet is so close to its star, the rocky surface on the planet K214b not just melts and form a giant magma ocean, but it also vaporizes that magma ocean, and you have essentially rock air that builds above this ocean. And we also found that this air will tend to blow away from the ocean, and the wind speed can reach up to 2 kilometers per second, and so that's many times the speed of sound on this planet. And it also follows a rocky hydrological cycle, such that rock melts and evaporates, and then in the air it condenses as well when it gets cool enough, and you get rock rain and then rock snow. So it has a quite active weather that is composed entirely of rocks. And
So,
and that's no, I was going to say that's all I have to say about it
what?
for introduction.
So, are you talking about like liquid rocks are raining?
Yep.
Whoa.
Yeah. So liquid rocks. And then essentially, I mean, this is speculative. When I talk about snow, and it may form snowflakes, because quartz actually has the same hexagonal structure as ice. So, but again, that's speculative. But it'll be cool to imagine, quartz snowflakes falling from the sky.
So let's break that down for a second. This planet was discovered in 2017 by Italian.
2018, or at least it was published in 2018. It
right.
Very well be possible that it was discovered before that. Like, oh my god, look at this planet through this telescope. We got to write it down, and we got to publish it. And the published date was 2018. So
gotcha. Yeah. And there's always because this paper, it's saying that it was, it's not supposed to be in March 2020 it was published. Is that right? When was this paper?
My paper?
Yeah.
No. So it was published in the day of the election, the U.S. election.
Okay.
So that's a very neat time landmark.
Yeah.
Land on, yeah.
We'll get there in a second, but how did they discover this planet? Tell us a little bit more about that. Like, what was the technology that they used?
Okay, so the name of the planet and the star actually tells you a bit about it. So K2 stands for the second phase of the Kepler mission. So Kepler was a orbital telescope that NASA sent out to pretty much catalog all the known exoplanets and to discover more exoplanets. So its job is there just to detect exoplanets and then record it,
Right.
and we build a catalog out of that. And so K214b is one of those star that has one of the orbiting planet, K2141b.
So, but just to clarify, K2141b is the planet, not the star.
Yeah, the star is K2141.
Gotcha.
Yeah, so every star that's discovered by Kepler is always, in the second phase at least, is always K2 and then some number.
Yeah.
It's like the order of the star they discovered or something like that.
What do you mean? What do they mean by phases? Like phases of exploration?
Oh, yeah. So funny thing about Kepler. So the original mission was just a Kepler mission, except what happened was that I think I forgot the name of like the system. So anyway, a satellite has a bunch of wheels in it, so that's how it orientates. And so what happens, like one of those wheels had a malfunction, and so the Kepler telescope couldn't direct at certain things. And so what happens is that the scientific community and people who operate this Kepler mission suddenly has like a different observation instrument, essentially, because it can't sort of point at something. So they have to implement certain ways to sort of salvage Kepler and just only detect certain things that they can detect.
Oh. So, sorry,
So that's the second phase of the Kepler mission. Yeah.
So something went wrong with the Kepler mission. That's why there's two phases.
Yeah. So it's internal mechanics.
Okay.
No, it's one of the motors.
So it had to come back to Earth.
No. It
Okay.
didn't. So it's just out there, and it's like we couldn't control it like
Right.
we used to, and so we have to build pretty much new objectives to salvage the fact that we still have somewhat functioning telescope out there in space.
Yeah, because how are you going to fix it? It's way out there, right?
Yeah.
So what they've done with the Kepler mission is they've kind of adjusted to, like, it's gone off course, I guess. Is that sort of what you're saying?
Well, you made it sound like it's just flying far away from its orbit. It's just that I think it can't orientate itself towards the target.
Oh.
Like we used to target, so I think it can still target, but it's like much harder. There's certain things you can't maneuver around, and so that's why they have to get new objectives.
When did they launch this satellite?
All right. Let me
Oh,
Google
sorry.
that. Because I don't really know. I only know that it was like somewhat. So 2009.
Oh, okay.
Yeah.
Yeah. So 2009 they launched this, and whereabouts is it right now? Is it?
I think it's been decommissioned.
Oh.
Actually, haven't heard from Kepler in a while, so I assume it's been decommissioned, just like Spitzer, another orbital telescope out there. So I think only Hubble is still up. And they're going to launch a new telescope. It's called the James Webb Space Telescope. So that's the big one.
Yeah.
That's going to launch. Oh yeah, and they also have a TESS, another NASA mission, or ESA. It's probably, they work in collaboration to get these missions out to observe exoplanets.
So the paper talks about the James Webb launch a little bit. What year is that scheduled for?
So I think it was designed. So it was designed in like either the 90s or the early 2000s. It was like supposed to launch in the mid 2000s, but now it's been delayed to October 2021. So next year. Yeah.
And this one is going to be like it.
Well, it's going to be huge.
Yeah.
That's what you want a telescope. And the important thing is that it can actually look at more wavelengths. and it can look at in particular the infrared wavelength, which is wavelengths that are longer than your red, so you can't see it with the human eye.
Right.
But it's a very good marker for detecting things like atmospheres.
Yeah, when it comes to the sort of like the this, you're gonna, I don't know what I'm talking about here, but the spectrometer or whatever, ultraviolet rays, those are the ones. Yeah, those are the ones that we can see. Ultraviolet.
Oh no, you can't see ultraviolet.
Okay.
But actually, butterflies can see ultraviolet, and apparently, it's how they can see things like nectar and sort of like liquids that blend very well into the background. I think evolutionary wasn't worth it for humans, I guess, to develop UV vision. It would be kind of cool if we did, but
So
yeah, so it's just the visible wavelength is what we see with our eyes.
Yes. Yeah.
So that's from red to blue.
So this James Webb telescope, it will be able to see not ultraviolet, but infrared.
Yeah, infrared.
What's so special about that? What?
So so infrared means it's a long wavelength. So a lot of it depends on just how warm something is, and something doesn't need to be as hot to produce infrared radiation.
Right.
As opposed to, say, white light, right? If you want to produce white light, you're gonna need a burning star to produce white light. So, getting deep red, you don't need, any fancy fusion or something like that. It's just something that needs to be somewhat warm to emit infrared.
So by having this, they'll be able to see where there could have been, dead stars, supernovas, things like that, to kind of get a sense of where there might be other planets, like.
So I know that so infrared is sort of used for things like clouds or like dust. It's like a lot of something that it doesn't produce its own heat, right? Mm-hmm. So it's hard for us to see. So the only way we can see is if it's reflecting existing light, right? But if you just use infrared, you can actually just see it because it emits some infrared radiation because it's not absolutely cold.
You actually just kind of made me think about something. Are there weather systems in space?
I would. Well, how would you define weather?
Yeah, that's a great point. I mean,
like weather. When you say in space, do you mean like in like a grand nebular Milky Way kind of thinking, or like on other planets? Like on Titan, is there weather systems on Titan?
Right. Well, in between planets, like in space, in the space between planets, right? I guess that's how you'd explain it. Are there weather systems? Because I mean, I think that they've seen like lightning or whatever in space.
Yeah. So if you, because here's the thing, the word weather has like an Earth-centric view to it. So if you consider lightning strikes on Earth to be part of the weather, which I think it is, and space, there's definitely spots that have lightnings in between nebular clouds. Maybe, I actually don't know for sure. If I had to bet, I'd bet that there is weather on space.
Yeah. Well, because we were talking a little bit about lightning storms and stuff, and lightning on Earth, doesn't it start from the ground and go up? Like it doesn't come from the cloud; it comes from the ground.
Oh, so it's random. It's randomized. Sometimes it goes up and sometimes it goes down. And so I think if it's random, so it should be half. So half the lightnings you see are going from the ground up.
Okay.
And then the other half going from the up down. But you can't see it because it travels so fast.
Yeah.
And all you can see is a line. It just appears and then disappears.
Right. Because they have seen in space that there's like lightning strikes or whatever in like gas nebulas or something like that. Isn't that true?
I actually don't know. That's a bit outside of my expertise.
Right.
That's more for the astronomy purist, which I'm not really. I'm just an Earth guy that's been kicked out of the solar system.
So going back to the hell planet, What are your thoughts on it getting that nickname? Do you like that nickname?
Well, I like that it has a nickname. That's a lot of press that
That
I'm,
is.
I'm not gonna neglect. I'm like, it's like, yeah, I'm thankful people are thinking about this. They're passionate enough to name it. But that's a yeah, I don't mind it. It's just funny to me that like I think CBS or no, I think Daily Mail, yeah, Daily Mail says like the most inhospitable planet we've ever discovered. And I was like, I don't know if that's true because like I don't think you want to live in the middle of Jupiter, or you can live in Neptune, or I don't know. What's the bar for most inhospitable planet? Right?
As far as I know, this is the only habitable planet. As far as I know, I mean Mars is you can't really live there unless you terraform it or whatever.
Yeah. So anyway, no, the press says crazy thing.
Yeah.
People see the word hell planet and they're like, oh, I'm clicking on that.
100%. I saw that. I'm like, that is incredibly heavy metal sounding. And then I look it up and it's like magma lake. So how did you find out that there's a magma lake?
Oh, it's a magma ocean.
Magma
Actually,
ocean. Excuse me.
No, I don't know. What's the difference between an ocean and a lake, though, when it's magma, right? Because I think on Earth it's like oceans are saltwater and lakes are freshwater.
Right.
Is that how it's defined?
Yeah.
So yeah, no, it's just the fact that it's just so hot on the surface. We predict it to be like 3,000 Kelvin. So that's
Holy.
It's like 2,800 degrees Celsius. And so that's enough to melt rocks, right? And
therefore,
and so and a lot of the surface is like, somewhere in that range too. And so we don't we can guess, we only guess, how deep the ocean is, which is like hundreds of kilometers if you just see, if it extends this heat and it goes all the way down, when does it compress enough to form a solid again? That's just liquid. And yeah, it's just that hot, man. That part, like a good chunk of the planet is just molten.
Now, you were talking earlier about how quickly it spins around the sun, its star, and that's how you were able to sort of figure this planet out. So how long is a year? Because a year is a full revolution around the sun, right? So how long is a year on this planet?
So K214b is tidally locked to its star, which means that its day is the same as its orbit. So the length of day is the same as the length of orbit, which is only 6.7 hours, or 6 to 7 hours, I think, is how I remember it. Yeah, somewhere around there.
Right.
So very fast. And yeah, so that's why it's easy to observe this, because it just goes throughout a day. You can see it transit 3 times, and the more you observe it, the more precise measurements you can get out of it.
So yeah, the more revolutions around its sun. So when they're looking at it through the telescope, they're not seeing the planet. Weren't they seeing like the atmosphere or something? That's what was reflecting the star.
No. So they just see like a bunch of pixels that are just the star.
Right.
And so whenever a planet passes, so that means it blocks some of the light from the star. As we look at it, the light from the stars dims.
Right.
And it dims and brightens in a very specific pattern, and that's how we can derive the orbit mechanics of our planet.
Okay. So how far away is this planet from its star?
Oh, it's like super close. I don't know the number off the top of my head, but it's even closer than Mercury to the sun. And so Mercury is the closest planet to the sun we have. And a trivia for you, it's actually not the hottest planet in our solar system. But yeah, so K214 is even closer to its star than Mercury, but I don't know the exact number. I'm sorry. And here's the thing, though. Here's the thing with like astronomical numbers. It's just so big right?
Yes.
And so anything you think of, like, say, like 1,000,000 kilometers, right? That's, to you, that's like an impossible distance to fathom. And then you just say twice of that, like twice of infinity is to infinity, right? It's
Yeah.
still going to be the biggest number you can imagine. So
Yeah.
there's no point of trying to.
It's hard for us to really conceptualize the metric of the distance,
Mhm.
right?
On a space scale,
Yeah.
right? Like, we're just monkeys.
Yeah.
It's just monkeys sitting on chairs, man.
So now Mercury is a gas planet, right?
It is not. It's
Oh,
rocky. So the four inner planet of the solar system are all rocky.
okay. Because I would have thought that this planet that's so close to its sun wouldn't be able to be a solid planet, like a rocky planet. It would. I think it'd just be a gas planet because it would just melt.
Yeah, but then you have a liquid planet. I don't know. Then you have an ocean planet. Well, here's the thing. So
Oh, okay. I see. Yeah, yeah.
no. But the thing too is that so planets are like huge too, and if you don't have an atmosphere, there's no way for the night side to be warm ever. And so the side of the planet that's facing away from the sun, it's
Yes.
actually super cold. It's like negative 200 degrees. So yeah,
Wow.
so I don't think being close to, and in fact, being close to the star makes it likelier that you're a rocky planet. I think there's some theory about solar system formation that prefer that kind of setup. And you also notice too that small planets tend to be closer to the star, and then big planets would be further out.
I wonder why that is.
Well, I got on for that, man.
This is but isn't that why this is so fascinating? Is because we really don't have answers.
Yeah. Or I think people have definitely have theories about it, and they probably have written it up too. There's probably some sort of community accepted idea of how the solar system formed,
right?
That I just don't know because it's just outside of my field
right.
again. Just a dude looking at clouds, man.
So you're talking about this planet, and you're speculating sort of how it looks, what its characteristics are. You use a number of mathematical formulas in your paper.
Mm-hmm.
What can you tell us about these formulas that you use?
Oh, so they're just simple. Well, no, I shouldn't say that word. They're just
They're not simple for me, I'll tell you that.
No. The correct word is elementary. I think that's the word mathematicians like to use. They're the elementary equations, and
Right.
they do have a name. It's the Navier-Stokes equations.
Okay.
So it's a popular field in math, so it just solves for what are called differential equations. So when you have your variables, so these are like your dimensions, things you want to know, like temperature, pressure, and wind speed, and they interact with each other in a different way. And so the mathematical model essentially tries to figure out, if the pressure and the wind speed is this, what's the temperature going to be, and it models fluid movement.
Oh, okay. Because that's what was kind of giving you a sense of what this planet was like, right?
Mm-hmm.
Yeah, because you were able, like, how were you able to figure out how fast the winds were?
Okay, yeah. So the winds on Earth are actually driven by pressure gradients.
Okay.
So if you check your local weather station, they say a high of something and then a low of something. Oh no,
Right.
that's for temperature. No, like if you look at when they do, like, say, tropical storms,
Yes.
and they have like
High
lows
and
that are
low
moving.
pressures. Yeah.
Yeah. So all sorts of wind speed is just driven by the pressure gradient. So highest pressure will move to low pressure.
Mm-hmm.
And so what we calculated was we calculated, the temperature is this, and so that means this much gas has to be vaporized given the temperature, And given our fluid model, right, we can calculate, how the pressure changes as you move away from the magma ocean. And so you would have a force that pushes the wind. You can actually imagine it sort of like you're building, like you're pushing something up a hill and then it rolls down a hill because there's like a mass difference, right? There's like heavy mass and it just falls.
Right. Right.
And so that's essentially what's driving the wind.
Whoa. So, but like, how does that tell us how fast it's going? You know what I mean? Because saying it's going, what was it, 2 miles?
2 kilometers per second.
2 kilometers per second. Holy like that's crazy.
Yeah, no, it's another number you can't conceptualize.
Yeah, good point. Yeah. I wonder what the margin of error is for something like that. Like,
it's probably like 2 kilometers plus minus 2 kilometers per second. It's 0 to 4.
Yeah. That's funny. Because, I mean, like I said, I find this stuff fascinating, but it's like you say, we're looking at it 200 years into the past, right? This is what it looked like 200 years ago. Now, the star that it's nearest, well, how old is our star? Because stars don't live forever, as we know.
I think so.
Isn't it like 4.5 billion years or something like that?
Yeah. So it's I think similar to the age of Earth, which is 4.6.
Okay.
Let me do a quick Google search. Yeah, 4.6.
That was not bad. That was not a bad guess. So our star is 4.5 billion years. First of all, how the hell did they figure that out? How old our star is?
I actually don't know. I think we may have known how old the Earth and the Moon is,
right.
And then we can just deduce that the sun couldn't have formed that much earlier than the Earth.
Yeah.
So I actually don't know how they know how old the sun is.
I gotta look that one up. But they are saying that our sun is expanding right now.
It is. Mm-hmm.
How much is it expanding a year? Sorry.
No. Every time there's a mouse click, you're like, oh, bro, you don't know. Yeah, okay. I'll just concede. I don't know.
But like, is it a big number?
No. It's actually, I don't know, because you're in the cosmos, right? So like a big number may seems like a small number in the grand scheme of things.
Yeah.
But totally. I do know that it'll take like millions of years at least for the sun to engulf Earth.
Yeah, which is crazy. Like,
why? That's so long ago.
Yeah,
that's so far into the future.
We need not worry about it.
Yeah, there's probably like an evolutionary change, like the humans are no longer the top of the food chain at that time.
We'll be somewhere else or nowhere at all. But what was I going to say? Yeah. So this star, are we able to kind of figure out where it is in its life cycle?
So it's actually probably very near the end of its life cycle, where it will just become a brown dwarf.
Okay.
Because it's actually its star is actually less brighter than our sun. So the star is actually relatively small compared to the sun, and it's not big enough for it to either go supernova or become a black hole, as you do with the typical, life of a star.
Right. Is a black? Sorry, go ahead.
No, you had a thought, but.
Well, I was going to say, is a black hole, is that a star? Like, is that a dead star?
Yeah, I think, actually, I don't know for sure, but I can guess that it's, I think it's what happened to a star after a supernova, I think, if there's some sort of remnants where the matter is so dense. The thing about black holes is that it doesn't have to be big. It just has to be so dense that the force of gravity is so strong that even light can't escape.
Well, I was reading in Stephen Hawking's book, and it was, what was it? It's like one of his shorter books.
Man,
which
if you
is
read Stephen Hawking, you know more about black holes than me. I haven't even read a word from Stephen
okay.
Hawking.
So he's saying that in the universe, there's tiny black holes, and then there's massive black holes. And it's better that you go through a massive black hole than a tiny one, because you're going to get sucked through the black hole like you're a strand of spaghetti. But you get pulled into it all the same as you would a massive black hole. As for what's on the other side of it, nobody knows. But it's like, I mean, when you start talking about that, you're just like, wow, how are we here right now? How have we not been swallowed up by one of these things?
Because I feel like if we can be swallowed up by these things, Earth probably already would have been swallowed up by these things.
That's a damn good point. That's a damn good point. I mean, maybe there's, yeah, wow. I have somebody on in a few weeks that's talking about black holes, so I'll stump her.
Yeah, she's like, oh, this dude knows nothing. You're gonna fill in all the gaps. He was saying that like black holes or what? Was after a supernova.
She's just gonna dismantle everything that I just said there and say that it's all wrong. So now,
hey, man, you quoted Stephen Hawking, so like
I paraphrased Stephen Hawking. I can't take no credit for this guy.
No, you cited it properly, so
thank you.
It's a convincing argument for the case of why you want to go through a bigger black hole, not a small black hole.
So in this paper, I mean, so much about it, like, yes, it's talking about this hell planet, of course, but it's saying implications for low and high resolution spectroscopy. So what's thank you, I can't pronounce words today. Anyways, what does that mean exactly?
Oh, so it means that we're going past just the phase of detecting it, and now we're going to go into more detailed observations. So that's so that's high resolution spectroscopy, and also low resolution, but you want it in like the infrared wavelength. So that's the future tech that we need to get to. But for standard spectroscopy, so it takes into account the Doppler effect, and so the Doppler effect is most known for us with sound, right? When a siren. A car with a siren that's going towards you, its sirens are going to go in a higher pitch frequency because the sound waves are packed in. But when it's driving away from you, the sound waves are spread out, and so you will hear a lower frequency, so it's going to sound lower. And the same thing happens with light as well. And so whenever you have a very strong wind speed, like 2 kilometers per second, and so the light that's traveling in that air, it's going to shift it by a little bit because of just how fast the medium is moving. And so that's one of the things we can detect, that we can measure with existing telescopes.
So, but what does that mean for this planet, though? That you're seeing, that's what you're seeing when it's spinning around the star?
Yeah, so what happens is that the light from the star that goes around the planet, it's going to change a little bit. The wavelength is going to change a little bit. And that's what the resolution in spectroscopy means. That means you can look at individual wavelengths of the light that's going through, and you see how much it shifts.
Right. So, and is that telling us how big the atmosphere is on this planet?
It tells you how fast the wind is, so it's a validation of
okay. And that's right. Okay. Yeah. Now, were you able to figure out if there's like an atmosphere on this planet?
Yeah. No, that's what our work is. That given what we know about the planet so far, it should have an atmosphere. Yeah. And this is what the atmosphere should be like.
Right. Because on Earth, like our atmosphere is, I think it's like, isn't it like 3 kilometers or something from the surface of the Earth to
space? It's much higher than that. It's like tens of kilometers of the atmosphere. Okay. So I mean, so in the atmosphere, it's like from Earth to space, there's different stages. There's the atmosphere, and that's composed of like the troposphere, and then upper troposphere, and then stratosphere and exospheres, things like that. So I guess if you consider the atmosphere to be something below the stratosphere, then you would say, you know, few kilometer.
Mhm.
But if you say from Earth to all the way to exosphere, it's like tens or hundreds of kilometers even.
Now on this planet, are you able to detect how big the
Oh yeah, so the planet, so the atmosphere on the planet is actually really thin.
okay. Yeah.
It's about 5 kilopascal, and Earth atmosphere is 100 kilopascal. So it's 5/100. Yes, it's 5% of Earth's atmosphere. So it's not very big.
Yeah. Because I'm wondering, like, could life exist on this planet? Obviously not anything like us, but like a single-celled organism, like a bacteria or something like that.
I think there would. I mean, because I said before, the day side is 3,000 Kelvin, but the
Right.
night side is like near zero. So there's gotta be like a Goldilocks band on the planet where the temperature is actually just right.
Oh yeah, that's a good point.
For things to live on. Yeah.
Yeah, I never thought about it because yeah, there's the super hot side, and then there's the super cold side. But because it's pretty constant, in between those two could be like, obviously not livable for you or me, but possibly for like a eukaryote or whatever, a prokaryote or whatever they're called.
Yeah,
Is
yeah.
is that something that you guys have considered or talked about?
Oh no, so that's more into like astrobiology. That's for
Dude, that sounds cool. Astrobiology.
yeah. It's they do a lot of search for extraterrestrial stuff. So they look for like biosignatures on distant planets. So things like methane gas. But I don't do any of that stuff.
Have you ever thought about doing anything like that?
Well, I mean, the thing with astrobiology is I feel like it's even more speculative than what I'm doing. It's like
That's a good point. Yeah.
because like I'm talking about this planet, but we haven't actually been observed it as closely.
Right.
So my paper is actually just making an argument that we should look at this even more closely
Mm.
to sort of understand just exoplanets in general. Because here's the thing, we actually haven't been able to find or detect a rocky planet's atmosphere before. So technology hasn't allowed us to do it yet. But with K214b is actually the best candidate to observe an atmosphere of a rocky planet outside the solar system.
What? Why is that?
Because so it actually has the fastest orbit that
So
we've
quick.
ever discovered. Yeah.
Mhm.
So the thing with a fast orbit is that we can look at it a lot when you do
You can see it 4 times in one day almost.
Yeah, exactly. So yeah, that's why, and it's pretty big too. So it dims a lot of light as opposed to like a smaller planet, So you see a bigger dip in the light coming in from a star.
That is pretty crazy. Now here's another speculative question for you. Do you think that there is life on other planets?
There's gotta be. Considering how big the cosmos is, right? It's
unfathomable. We cannot fathom how big the cosmos is.
yeah.
Right?
I can't fathom a plane ride from Sydney to LA. There's no way I can fathom how many planets there are in the universe.
There's a great quote out there. I forget what it is, but there's this game called XCOM, and at the beginning of it, there's this quote, and it says,
I played it.
Yeah, it's like either we are alone in the universe or we're not, but both conclusions are disturbing.
Equally terrifying.
Equally terrifying. Yeah, and you think about that, and you're like, yeah, that's completely correct. And the other thing is that what life would look like on other planets, there's no way it would look like what we look like, because it would adapt to whatever its environment is. Kind of like in Australia, you have kangaroos, right? This is Neil deGrasse Tyson that I'm now paraphrasing. So in Australia, you have kangaroos, but here in North America, you have deers. But at one time, or deer, excuse me, deer. But at one time when it was Pangea, it was all together, whatever, blah, blah, blah. And then they separated, the continents split apart, those animals adapted. So whatever life we would find would be adapted to the planet it's on.
Yeah, you got it, man. I'm not doubting anything you say.
Yeah. But like that's, I don't know. Like, so we find life on another planet, then what?
Oh, then I lose my job. Mission accomplished. Bye. I'm gonna flip burgers and Mickey D's now. That's
How did you get into this?
Yeah, so I was actually studied to become a weatherman, and this was at McGill. And when I applied for grad school, because I wanted to explore, weather systems even more, because it's pretty cool. I was really into storms. And then actually, there's a lot of dedicated storm chasers among people who do what I do. And then so I applied, and then randomly this York professor asked me if I want to study the weather on Mars, and I was like, "Yo, I want to tell people I study the weather on Mars, and I'll do that. Yeah, and so that's what I did. And then next thing you know, he's like, "Hey Zhang, how you like studying the weather on planets outside the solar system?" I'm like, "Whoa,
yeah,
that's so underground."
Okay, stop right there. Yeah. So other than K2141b, what other planets, and other than Mars, of course, what other planets have you looked at?
No, that's it.
Okay, so you're just getting started.
Yeah. Well, I mean, it took me like a couple years to pump out this publication back when I was just an infant baby. It's like, "Hey Zhang, what are you doing this summer?" It's like, yeah. So it took quite a while, and we're still looking at it even further. So my paper is actually being used for a proposal.
Okay.
So when James Webb launch, we want X amount of hours to look at this planet, and we have to compete with other scientists. They're like, "Oh, we have a cooler planet than you. This one has like a blue ocean." So it's like so we gotta make a convincing argument that K2141b is, in the very least, a very interesting case to look at.
So James Webb is overseen by NASA.
No, that's correct.
Right. So you'll submit this paper to NASA to try and get so many hours.
Well, here's the thing, though. So it's not entirely funded by NASA. So different space agencies actually have different requirements for participation in the James Webb Telescope. So the European Space Agency, their job is just to launch it. Like that's all they have to do. But like other countries like Canada, we build specific instruments on the James Webb Telescope. And because we built specific instruments, so Canadians actually have an allotted amount of time for observations, as does other countries that has contributed to the James Webb Space Telescope.
Who controls the most of James Webb, and it's sort of, oversees what it's going to do?
If I had to take a guess, I don't know for sure, but I'm almost certain it's the U.S. It's never not the U.S. The U.S. contribution to space exploration is unrivaled, I think. Up until very recently, now that you got China going in the fray, and you also have private entities like SpaceX and Blue Origin trying to get into space.
Yeah, because NASA is still a government, like it's a federal thing, right?
It's a public institution.
Yeah, whereas SpaceX and what's Jeff Bezos's one?
Blue Origin.
Blue Origin, yeah. So they could do whatever they want.
So I think they still have to follow space regulations. I think.
Oh.
Well, because here's the thing with rockets, 99% of the things we've ever strapped onto a rocket is a bomb. So so that's why that's why space launch is actually very heavily regulated.
Right.
Because governments don't want people just launching random things.
Fair enough.
Terrible implications.
Yeah. Also the amount of like detritus that gets stuck in the atmosphere, spinning around. Like there's tons of space garbage from all the launchings.
Yeah, space debris.
Yeah, space debris. And I heard that in China, going back to your shooting rockets, bombs off, they had a launch pad and it's like right beside a major city or something like that. And that was like a huge controversy. I don't know if you ever heard of this.
No, I haven't.
Yeah.
It doesn't surprise me that China would build. It's more convenient, right? You can just walk to work. That's
the commute's awesome. Yeah. So I guess it's like, well, what's next for you? You're going to keep trying to get these proposals in and
yeah, so I'm also trying to go into more modeling of icy planets. So they're like snowball Earths that may exist out there, and how we may be able to detect them. But that's also, yeah, so what I do is also very dependent on future technology, right? And I don't know what's tomorrow holds.
Right. But you'll always have a job.
I don't know, dude. Like, I guess I can always teach,
Right.
That's what all grad students tell themselves. At least I can teach.
So you're done being, are you going in your doctorate program right now?
So yeah, I'm in my doctorate program. Okay. I'm going to graduate in 2 years. So I have 2 years before I regretted not looking for a job during the 2 years that I
had. and is this your thesis statement, this K2141b?
So it's a good chunk of it. Yeah. So So simple model of K214b, and then more physics. That's my next project, or my current project right now.
Yeah.
And then it's the icy planets, icy Earths. So Earth-sized planet that are formed of ice, and so the ice will form an atmosphere of water vapor, and that might be observable through the James Webb Space Telescope. It has a very important job to do. A lot of expectations for that mission.
Well, I'm sure you'll pull through. I definitely. So they're launching in 2020, October 2021.
Yeah, that's what Google tells me.
Okay, I definitely want to hear more about this. So,
dude, it's huge news. Just Google James Webb Space Telescope. There's a lot of people talking about it. As I said, it's like a $20 billion mission. A lot of eggs in this one basket right here.
Wow. And it's launching from Europe. Is that correct?
No. So European Space Agency is going to take over the job of launching it.
Yeah. So they're mission control. They're mission control. Yeah.
But the thing with launches actually is that you want to launch as close to the equator as possible.
Because it's less rotation, right?
Yeah. So there's something about the angular momentum of Earth's orbit, and so I think
the Coriolis effect or whatever.
Actually, the Coriolis effect, it's more prominent on the when you're closer to the poles.
Right.
But I think on the equator is actually where the Earth spins the fastest, and I think that's why they want to launch it there, because it has like more angular momentum to orientate itself into space
and get further out and just keep going, right?
Yeah. So I think that's why U.S. launches is in Florida, right? It's like one of the southernmost. I don't know if it's the southernmost state though. I wonder if Texas is more southern than Florida. I don't know. The U.S. is a mystery.
Still to this day. Yeah. Well, Giang, thank you so much for telling us about your research and the Hell Planet. And I look forward to hearing from you again as more research comes out. So, keep pumping these papers out, man, because people are definitely interested. Did you know that you're going to get this much buzz from this planet?
Oh, no, not at all. Well, I mean, and to be honest, it's actually very little of my doing. One of my supervisors, Nick Cowan, he's the second name in the paper.
Yeah.
He was like super on it with the press release. He was like, "Yo, we're gonna set out a press release. We're gonna talk to the reporters."
Yeah.
Actually, no, I regretted not posting it to Reddit or Twitter or anything. I was low key about the whole project.
Well, you're
let the work do the talk,
Well, like I said, man, this is fascinating stuff. So keep it up, and I look forward to hearing from you again.
All right, for sure.
All
Thanks
right.
for having me.
Thank you, Zhang.
Take care.
And I didn't lose you this time.
Yeah, both our internet, we're good.
There you go. Okay, man. Well, hey, you take care, and we'll keep in touch. All right.
All right.